our special substitution is going to generalize to the idea of the Jacobian. And Jacobian is a special, I mean, just the name itself is kind of cool, right? It's going to be a special way to change coordinate systems, and we're only going to really look at these three changes of coordinate systems, although many other exist, and many others could depend on the integral that you're working with, but you know, we'll focus on these. Yeah. The Jacobian technically is the last section in this chapter, but I wasn't planning to cover too many things from that section, and so what I wanted to do was just get the idea of the Jacobian and justify why there's an R in the dr d theta. So that's all I wanted to do, and I'm not gonna officially test you on it, but I just want to use this as justification and like a jumping board. Is that what it's called? Diving board, jumping ramp, a ramp onto talking about triple integrals in cylindrical and spherical coordinates. Okay, so let's talk briefly about the Jacobian, and I'm not going to do this in that much rigor. I'm not going to be that rigorous in it, but what I want to do is just talk about the idea of the Jacobian and give you a neat compact formula for it, and then move on. So let's talk about the Jacobian. And before we come up with just the formula, let's think of what's actually happening here. Well, actually, sorry, before we do that, let's do a recall. Trig sub or U sub, let's do a trig substitution. And back in calculus 2, question? The last section in this chapter. 10? Yeah. 15 last. So again, this section 1510 will not be on the test. We're just using the information from there. So there's other things that we can discuss in 1510 that that could be interesting too. But I'm really wanting to just use 1510 information to derive some of the formulas that that allow us to do the transformation from one coordinate system to another. So back in Calc 2, what we did was trig substitution or U substitution, trig sub. I think U sub. I think let's do U sub. So when we're integrating x e to the minus x squared dx, for example, from 0 to 1, or 0 to 1, we're going to say let's let u equal to minus x squared, and then du is equal to minus 2x dx. And so we do the substitution, we come up with a differential. And this is your differential here with a dx next to it. And then we also sometimes, or very rarely now, but the theory behind it is that we can change the limits of integration as well. So we change the limits of integration. U of 1 is equal to, I think it's -1. U of 0 is 0. So we change the limits of integration, and now our integral becomes a double, or not a double integral, just a single integral. I think there's a -1/2 that comes out, e to the u du from 0 to -1. So we do this change of variables, and inside of the integrand, we change the variable, and then we also look at the limit, and then we change the limit. Okay, so that's how we did it back then. And so with this as the key to our starting, the key to our changing the variables, and well, let's see if we can see what happens when we change the variables in double integrals. So with double integrals, when you're doing this Jacobian using double integrals, I didn't need to do that. We're looking at x is equal to r cosine theta and y is equal to r sine theta, right? And so what we want to do is we want to, aside from dealing with what's happening here, we want to take a look at the limits of integration. Well, I guess in terms of a triple or double integral, right, where we have a dA, dx, dy, our limits of integration is really dependent on r, right? So this is your r, whatever r is. And with this substitution, what we're doing is we're going to transform our integral into something with an r and theta instead of an x and a y. And so your limits of integration, so to speak, or what you're integrating over is going to change, and hopefully going to change for the better. Let's call this one d. I think they call it r star or something, but anyways, we'll call it d. And hopefully it's something easier to deal with. And then our function also changes. Instead of x, we have r cosine theta. Instead of y, we have r sine theta. Now the question is, what happens to the dA? dA, which used to be dx dy, or dy dx in some sort of order, has to change into something with a dr and a d theta in some certain order with some sort of derivative that's involved, right? Because that's what happened over here when we did a u substitution. We have to take a look at these differentials and how they morph from one domain to another domain. And so what I want to do here now is to introduce this derivative of this transformation. So this transformation has xy and r theta. So how many derivatives do you think are going to be involved there? Like 4 derivatives, right? So if we look at x as a function of r and theta and y as a function of r and theta, that looks like 4 derivatives. Partial of x with respect to r, partial of, well, let's write it all down. Partial of x with respect to r, partial of x with respect to theta. Oh, why don't we write it down like this? Partial of y with respect to r, partial of y with respect to theta. Okay. Why do you think I wrote it like this? What does it look like, say, if I put some brackets strategically? Close. What? Tree? No, it's like the chain rule. No, not quite the chain rule. What? probably look like a matrix. And then if we take the determinant of this matrix, that is how we're going to represent our derivative. Okay, so let's be specific about what we're doing here. We're doing the polar coordinate transformation. So let's take a look at our r and theta. X, let's take our derivative of x with respect to r. What's that going to be? Partial of x with respect to r. Theta is constant. It's what? No, that's the integral derivative. So it's just cosine theta. The r is just the variable, right? It's like saying 2r, the derivative of 2r is just 2. What's the derivative of x with respect to theta? R is a constant. Are you guys with me? What's the derivative of x with respect to theta? Well, this is x right here, the derivative of x with respect to theta. Negative r sine theta, right? Right? With me. Stay with me. Now let's take the derivative of y with respect to r. Just sine theta. And then the derivative of that same y with respect to theta. R cosine theta. Okay. So now the derivative of all the four derivatives that we can possibly come up with are all here, and we can represent that as a matrix. Now we want a scalar type thing to go into our Jacobian, into our differential, and so we would probably take the determinant to get the scalar out of this. So if we take the determinant of this, remember how to take the determinant? You multiply the diagonals and then you subtract the product of the wings. So what do we have? We have r cosine times cosine minus negative r sine theta times sine theta, right? So factor out the r, sine squared plus cosine squared is 1, and there is your Jacobian, r. So I know we justified having that r in our polar coordinate transformations using some geometry, and we looked at the sector or something like that and how the area changed. But more generally, you can do this using the Jacobian. So this is known as Jacobian. Jacobian of a transformation x equals some function of u and v. Is that okay, or should I use r and theta? I want to make it general. What? U and v? So assuming that x and y are functions of u and v, then we do this transformation, yeah? Because the derivative, because we're subtracting. We subtracted a negative of that, and so it became positive. So the Jacobian of transformation is going to be given by the determinant. Sometimes they call it J. equals, and then the partial of x with respect to u, partial of x with respect to v, partial of the second variable with respect to u, partial of the second variable with respect to the other independent variable. And the takeaway from here isn't necessarily to make the integrand easier to deal with, which is what we used to do with the u substitution, but it also means that your transformation from xy going into the new transformation uv, where you might have some complicated transformation here, r, and then this is an easier transformation. Let's make it a rectangle, d. That makes these limits of integration easier, hopefully, than what we had before. Whereas before we had like circles or pieces of circles, and now we have rectangles, constant limits. Okay, so that's the story behind this R that we've been using all along. Questions? And as an example, of course, when we do some sort of integral with a circle in there, so if R is equal to a circle, a radius 1, for example, then we change our double integral to polar coordinates, and we simplify your x squared plus y squared, and then your dA becomes r d theta, and then now your limits of integration, instead of going through this circle, you're going to have an easier set of limits to deal with. And whenever you have rectangular limits, you're looking at constant limits of integration. When you have constants of limits of integration, you could do a lot of other things like Fubini's theorem, where you can switch the order or even take out each of those if you can, and then that's going to make your computation a lot easier to deal with. Okay, that's the general story behind the Jacobian. And so now, as we start looking at more complicated double or triple integrals, we're going to be able to change coordinate systems into something that's more convenient for us. Where are we? Focus, focus. So now, let's go to section 15.8. Where we're looking at a cylindrical coordinate transformation. This will help us do things in 3 dimensions. And if you kind of notice, you got the r cosine theta and r sine theta. That setup is kind of like the the setup for polar coordinates. So this is really just polar coordinates, and the z is still going to be a z. So that's not really going to change things very much. So before we do an example of this, let's see how we're going to change our integral, our integrand, and our limits of integration, and more importantly, the dv, the Jacobian, what the Jacobian is going to be. So we have our typical integral. Where we have a dv, and the dv is like dx, dy, dz in whatever order that might be given to you. And so if we're going to change this into cylindrical coordinates, what we're going to do is we need to change our dv into something else. And for that, let's figure out the Jacobian. So now we have three variables. So your Jacobian should be a 3 by 3 matrix. So that's the partial of x with respect to the first variable, partial of x with respect to the second variable, and z is equal to z, so let's just say the partial of x with respect to z. And then we fill out the rest of the variables with all the possible first derivatives between these two sets of variables. dz dr, dz d theta, and dz dz. So specifically for these cylindrical coordinates, what we have is a 3 by 3 matrix. So derivative of, actually these four values over here, since they're coming from polar coordinates, so it can be exactly the same as polar coordinates, right? And I think that was cosine theta, negative r sine theta. This is sine theta, positive r cosine theta. So we just need to fill in the rest of the stuff. So I'm looking at the x function over here, and I want the derivative of that with respect to z. What's the derivative of that with respect to z? There are no z values, right? So it's a derivative of that with respect to z? 0. Same with the second one, dy dz. The derivative of this with respect to z is also 0. Now let's take a look at z, which is equal to z. The derivative of z with respect to r. There's no r's there. The derivative of z with respect to theta. There's no theta's there. The derivative of z with respect to z. I think that's going to be 1. Okay. So what you can do is you can use like what we did for the cross product to find the determinant of a 3 by 3 matrix. But instead of that, I'm going to use some fancier linear algebra where I, quote, expand on a row or column. I can expand on a row or column. So let's say I decide to expand on the last column. Or the last row. Expanding on the last row. So I have to assign signs to each of these things, and I want to expand all the elements in that last row. So my signs are going to be positive, negative, and positive. Each of those components has a sign associated with it. And it starts with the upper left-hand corner with a plus, and every time you move left or right, up, down, it's going to change. You don't move diagonal, by the way. So I would have 0, positive 0, times, it's not going to matter because it's 0, but what I would do is I would cross out the row in the column that it belongs in, and then I look at this little sub matrix associated with it and find the determinant of that 2 by 2 matrix. That's going to be 0. Minus 0 times another set of values that came from the matrix, plus 1 times that stuff that we've seen before. And we already saw that. That happens to be r, and so we have 1 times r is r. So our Jacobian for the cylindrical coordinate transformation is also going to be r. Think, wow, that's what was that all about? Why did we bother doing that? Well, so we can find the Jacobian. So our cylindrical coordinate transformation is going to give us a new integral now. So from the triple integral of E of f of x, y, z dv, we're going to be able to go to E star, which is going to be the new region that you're going to be dealing with, which hopefully will be easier. Then the function, and then except instead of x being x, it has to change into something with r, theta, and z. So that's r cosine theta. Y is going to be r sine theta, and z is still going to be z. And then our dv now will change to our Jacobian. And then any combination of, and then from here on out, when I write dz, dr, d theta, that could be written in any way. It just happens that most of the time we use z first, and then we use r and theta. Okay, but technically you could switch around. Okay, so this is our cylindrical coordinate transformation. Again, not a big change from polar coordinates because we have the same Jacobian, r. And then we tack on a z component, which just seems like it's silly. Why just have the z component? What's the big deal? But maybe this will be a little bit more relevant when we go to another changing variables that's beyond just the polar coordinates. All right, so let's do an example. Are there any examples here? Oh no, there's no examples. Pull out a book. We are in section 15.8. Wait, this is spherical. Maybe it's 15. Uh-oh. We might have gotten our sections. What? Let's try number 17, maybe. So we're here. We have an integrand of x squared plus y squared. A region lies within inside of the cylinder, and between the planes z is equal to -5 and +4. So this x squared plus y squared is technically a function of x, y, and z. And so that's not something that we would be able to visualize. And what we're doing is we're visualizing the region which is inside of the cylinder and between a couple of planes. So that's a fairly easy easy solid to visualize. And normally whenever you do these triple integrals, after if you're doing x, y, z, or even cylindrical coordinates, after you take care of the z component, you kind of just have to look at it from the top and see what the polar coordinate shadow, what the polar coordinate shadow is on the xy plane, which in this case is a circle. So I think that makes our job or this particular problem fairly easy. When we're doing a triple integral here, our region is that solid. We're integrating over that solid. And then this thing over here, we can think of that as like a density. Maybe that's a density of particles or something that's within the cylinder. It looks like the further you go out, the higher the density is going to be. And close to the middle, there's zero density right at the middle of it. And so that's one way to think about it. So now what we're going to do is, instead of looking at it the way we're looking at it with a cylinder, we're going to look at it as z going from -5 to 5, and then x and y is going to change into r and theta, where r is going to go from 0 to 1 or 4. Looks like it's going to be 4. And theta goes all the way around to 2 pi. So z in this case happens to be constant, so we can just put in the -5z for z and then +4 for the top limit for z. And then this is our new, we would call this E star, and we wouldn't really bother drawing it, but if you were to draw it, it would be a nice rectangular box, because it's just going to be restricted to constants. Anyways, the integrand will change. X squared plus y squared is equal to r squared in polar and in cylindrical coordinates. And then your dv is going to be r. And then you have a dz, which goes from -5 to 4. And then dr, it goes from 0 to 4. And d theta goes from 0 to 2 pi. Okay, so this integral is pretty easy to manage, right? We don't have to do it, do we? All right, maybe I'll do it later. Let's try to see if we can find another problem. volume, volume, volume. There's no mass, center of mass business. Number 19 looks interesting. Let's take a look at that. So evaluate the triple integral, x plus y plus z. So we're going to need to change that into its appropriate substitutions. Where E is a solid in the first octant that lies under the paraboloid. Ooh. So I think this paraboloid is upside down and it's raised up 4 units. And I need more information about the paraboloid, like maybe where it hits the xy plane. And then I also want to be conscious of the idea that this is in the first octant only. And so that probably means in the first quadrant in terms of my xy, right? So I want to see the shadow that this is going to make on the xy plane, and it's going to be some sort of, I'm assuming it's some sort of circle that's going to hit the xy plane. I just need to know what the radius is. How do you think can I find the intersection of this paraboloid with the xy plane? So z is equal to 0. If you said z is equal to 0, we have circle of radius 2, right? X squared plus y squared is equal to 4. So we know that these are going to be 2. Okay. All right. So we're pretty much set to figure out our E, our solid. We're going to find limits for z and then r and theta. So z is going to go from where? It's in the first octant, so I'm assuming the 0 is going to be the lower limit for that. And what's the upper limit? The paraboloid, right? I'm going to write it up here for a minute. Because why? Because what? It's not in terms of r and theta. So minus x squared minus y squared, put that together, what is that? So that is your first limit, and that is in polar coordinates. And then now r just goes from 0 to 2, it looks like that's the radius, and theta goes from where to where? Pi over 2. There you go, you're all set. All right, so our integral is going to be a triple integral. We have x and y and z, so I think we're going to have to write whatever x is, r cosine theta, plus r sine theta, plus z is equal to z, so that just stays z. So that's the integrand. Maybe we'll make a note of that. And then our d theta, or dv, is going to be that Jacobian that pops out, r. And then we integrate, I think we want to integrate with respect to z first. The order can change, can be flexible, but if z is a function of r, like in this case, the limits, you can't switch your r and your z. So you have to be careful about the iteration that you're doing. But like I said, most of the time, 95% of the time we're doing Z first. Shane? I converted to polar because of because of the solid itself. It's easier to describe in polar. Notice the x plus y plus z. There is nothing polar about that, and so we're more conscientious about the solid, what we're integrating over, as our motivation for the different system. All right, so z goes from 0 to 4 minus r squared. R goes from 0 to 2, and theta goes from 0 to pi over 2. Okay. It looks complicated, but it's probably manageable. The first one is going to be z plus z squared, or z times a big whole mess times plus z squared. And then you put in 0 and that, and then you integrate the rest of them. Yeah. It's what? Yes, it's pi over 2 because we're stopping here. Otherwise, if it was like first and second octants, then we're going to go to pi. If it's the whole thing, then we're going to go to 2 pi. Say it again. It is. I just didn't give myself enough room for dv. Yeah. Comes as a package. Okay. I invite you to integrate this in your own time. Let's move on. Now, there's some motivation. I could give you an example where I say, oh, it's hard. We could do it in the cylindrical coordinates, but maybe another system would be good. But let's just jump into that other system. So let's go into spherical coordinates. This is a little bit more complicated. No, just a little bit. Say again? Yeah. Or 8. I guess. I don't know. Yeah. So you guys have to negotiate the sections here because I'm going by an older edition of the book, I guess. So so if you could just soak in these these equations for a minute, and then we'll take a look at the graphics of it. Because I'll tell you in a minute. So spherical coordinates, as the name may suggest, would cater very well with spheres. Cylindrical coordinates would probably cater very well with cylinders. So as a sphere, as a cylinder, you got r and theta happening in 2 dimensions in polar coordinates. And so the extension between polar coordinates and cylindrical coordinates is the same r and theta, and then it just shoots up with an extra variable z. With spherical coordinates, what they had to do is they had to actually readjust the variables to cater for the fact that we were going to want to deal with spheres. So in the spherical coordinate system, you have x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho sine phi. So let's see what those variables mean and how they fit into coming out of Cartesian coordinates. So what we could do is take a random point in space. We can take a look at its shadow on the xy plane. And then let's take a look at the pieces of information that we're given here. The x, the y, and the z, where it comes from. And so now let's take a step from Cartesian coordinates and take a look at this from a cylindrical coordinate point of view. And the cylindrical coordinate point of view gives you a measurement of a distance from the origin to that two-dimensional point. So we're still on the two-dimensional point. And then it gives you an angle from the positive x-axis, theta. And then it gives you the height of that point is z. Okay. Now when we're dealing with spherical coordinates, what we're interested in is the actual distance, not from the origin to the point in 2 dimensions, but from the origin to the actual point. And because little r for radius is already taken, and they didn't want to use big R, they actually use rho as the variable to represent the distance from the origin to that point in space. So remember that r is a distance, it's a distance from the origin to the two-dimensional point, the shadow, and rho is a distance from the origin to the three-dimensional point itself. So we see rho, that's what rho is going to be. We see theta, and so that's the same theta that we're going to use that was used in cylindrical coordinates. So now there's this angle phi. So what is phi? Phi is an angle measurement from the positive z-axis. So rho equals a three-dimensional distance from origin to the point. Theta, same as in polar or cylindrical. And phi is the angle from positive z-axis. Okay, so that's what phi is measuring. So so how are we going to change this x, y, z into this other stuff? What they do is they take a look at this. There's kind of a cut looking at it at an angle. Let me see if I can rephrase this angle over here. I'm trying to look at, this is a positive z-axis. This is your measurement rho to that point. And this what is this distance here? What? R. Do you see how that changed? This is R, and this is phi. Okay, so looking at it from a slice, from an angle point of view, we got the positive z-axis here, and the angle drops down phi to that point. And so that measurement, that height of that point is going to be the z that you're looking for. And then we happen to have that r down there. It's all set up, right? What is z equal to in this picture? Is that a good question? Cosine, adjacent over hypotenuse, right? So according to this picture, cosine of phi is equal to the adjacent side over the hypotenuse side. So if you solve for z, z is equal to rho sine phi. Nice. Yeah. Why is it sine? Cosine phi, thanks. Yeah, look, r's sitting there. Let's just solve for r. What the heck? Wait, phi's on the other side now. Oh, wait. This is phi also, right? Is it not? Something to do with some geometry and like parallel lines and crossing lines. Something like that. That's phi. Can you tell me what r is equal to? Or let's use the sine of phi, right? Sine of phi looks like it's going to be opposite over hypotenuse. Well, let's think back to polar coordinates. The x and the y were represented in polar coordinates as r cosine theta and r sine theta. Guess what? You just found r. What's r equal to? Rho sine phi cosine theta, your x. Rho sine phi sine theta, your y. Here is your polar or spherical coordinate transformation. So how do you remember this? I just remember that the y is a sine in sine. That's all I remember. Oh, and I remember that z is a cosine phi. So from that you can work it out. So find a way to memorize it. Because you might not have notes on the test. What? I know, we're going to split the test in half. No. There's no shorter test. In fact, I'm all excited now. A 2-day test. This is really exciting. The test will be on it's gonna be fun. Thursday, a week from today, and Tuesday, because Monday's a holiday. Thursday next week and Tuesday the following. Not yet. Okay, wait. Let's finish this. I guess we're done with this. So let's just do it. Oh, Jacobian. So what we need to do is we need to have a combination of the r, the phi, or rho, phi, and theta And so, and then we have the x, the y, and the z. So we have the Jacobian is going to be partial of x with respect to rho, partial of x with respect to phi, partial of x with respect to theta, partial of y with respect to rho, partial of y with respect to phi, partial of y with respect to theta. Oh boy. 9 of them. So you need to take the partial derivative of x with respect to rho, and then take the partial derivative x with respect to phi, and then take the derivative of that with respect to theta, and then do that for y and z as well. And then you have to take the determinant, and the determinant is going to have all kinds of sines and cosines. Fortunately, a lot of those sines and cosines will just like, buddy up with sine squareds and cosine squareds and become 1. And then in the end, dot, dot, dot equals rho squared sine phi. It is a big mess. I encourage you to at least look at it and see how it's derived and see how a bunch of sine squareds and cosine squareds get together and disappear, and then how it reduces to this. So your dv now has a different Jacobian. Okay? All right, so I was fiddling around. Next week, I'm going to work on the grading scale to just be A, B, C without the plus and minus, right? Which means if you get an 89.9, you're going to get a B in the class. Okay? Somebody had come up to me and suggested or asked if they can base their whole grade on the final exam and nothing else. I have done that in the past. And so when I do it, I have to announce it to the rest of the students. I don't like doing it, but I have to announce it to everybody. If you're interested in that deal, we have to sign a contract before the next test. Okay? So the exam, oh, where is it? Oh, it's right here. I started doodling in my notebook, and the exam on Thursday will be the exam that allows you to use one sheet of notes, calculators, and computers. You can use Wolfram Alpha, you can use Desmos, you can use CalcPlot 3D, and these computers will be available on the outside if you don't have a computer on your own. Okay? So that is part 1 of the test, computational part. On Tuesday, the following week, will be the theoretical problems. Okay? I will post this in Canvas, or if you guys want to take a picture of it, go ahead. I tried to give themes and ideas, and for each of those themes and ideas, there are corresponding problems in the textbook that I looked at that looked good, and I might choose from one of those. Okay? Now, shorter tests, clearly, not every single one of these things are going to be on the test. So I might, for the first column, I'm probably just going to pick 5 of them. And for the second column, I'll probably pick about 5 also. Okay? The second column will not use calculators or computations. It's all about setting up the integral and leaving it alone. You might need to draw, sketch 2-dimensional stuff, but I'm not going to expect you to try to visualize 3D stuff with that. Okay? Yeah. The lines in the middle is the chapter 14 up on top, chapter 15 in the bottom. Yeah. I'm still thinking about that. This might be an index card thing instead of a whole page of notes. So concept checks. At the end of chapter 14 and 15, there are concept checks. They're just asking you questions to explain things, having you do true-false questions. I encourage you to really look at those and get to know the theory. And you could do that now this weekend so that you can get ahead with that stuff. You can do the homework to make sure you're able to do the computational parts. And then if you feel like you need more practice, there's more problems to practice with. Okay? Yes. This is going to be the review sheet. All those problems over there. So if I was to make the review sheet, I would just take all those problems and write it down. But you guys have the book, so I'm not going to write it down. Okay? Are there any questions? Okay, this is exciting. Good luck. Happy Halloween. Computer. So I called the office and they said that they can put you. I need to resign your form so that they can put you in like a media lab. They call it. Oh, do you? Where's our computers around? Okay, then that's it. Yeah. Oh, I'm just saying I'm giving you this now so you can prepare over the